that's really a forest project, but it has to do with acidity and acidification. And I won't sort of get into the nitty gritty of the technical parts, but just really some eye candy about what the project was and is and what we were attempting to do. If we have time, I'll keep my eye on Dr. Calderwood here in case she starts to snarl at me I'm running over. So be sure I'm serious, be sure you let me know how we're doing on time. So with that, then start with a pretty picture of different soil profiles, and going to talk specifically about pH. We talk a lot about pH. We get our soils tested for pH. We get our water tested for pH. The folks in Flint, Michigan, wish they had tested for pH before they started to change their plumbing. It's really an important variable. It's kind of a master variable. We use it in human health, and we use it in soils, but ecosystems, what have you. My background, I am a soil scientist, a biogeochemist. I've sort of been trained and worked in ag and forest soils. A lot of my research has been more focused on forest soils. So I know just enough to be dangerous in other sort of settings. So first, what is pH? And this is actually one of the pop quizzes I use, or one of the slides I use with my my students. I know you all know that the first three are not the right answer for what is pH. But pH is literally defined, formally defined as the negative logarithm of the hydrogen ion activity in solution. Because tonight we're sort of talking about pH and acidity specifically, I thought it'd be useful to start with the formal understanding of what that means. And it's really a measure of how much hydrogen is around, which is the acidity that we're talking about. But the difference between concentration and activity is important in sort of some of the chemical world and some of the biological world. And a pH measurement actually is a measurement of activity, not concentration, although for practical purposes, it's fine. Either one works. And so what's the difference between, can you see this bar at the top? Can you see my whole slide, or do you see my?
I can see activity versus concentration, and that's the top of the slide.
Okay, because I've got this. Oh, I can move it over here. There we go. I had my control bar popped up over there, blocking it. Okay, yeah. Thank you. So here we have a beaker, and let's say this is a certain amount of hydrogen. And it kind of represents the concentration. And without using units for the moment, it's one hydrogen that's here, and everything else is just water in the bottom of the beaker. And in this case, concentration and activity are identical because there's just that one hydrogen. However, if we looked at that same amount of hydrogen in another system, how am I going to do this? Here's another beaker, and there's our hydrogen. We still have just one hydrogen here, but there's a whole bunch of other stuff, lots of other ions or solutes or things dissolved in the water. And in that case, the concentration is still the same. We still have the same absolute amount of hydrogen, but the activity would be slightly less, because the activity is what we sort of refer to as the effective concentration. In other words, in chemical reactions and for plant roots and for microbes, what they can see as far as the amount of any ion that's there, a nutrient, hydrogen, is a function of, truly a function of the activity, not the concentration. And in fact, when we measure pH, and probably everyone here is familiar with how we do that with a variety of ways, actually, but with a pH electrode, a little glass electrode, and the glass at the bottom of the electrode is selective for hydrogen, but it's selected for hydrogen activity, not the concentration. So from the standpoint of what is pH in the chemical world, formally a representation of, as a symbol, it's a representation of the activity. In most natural solutions, like soil solutions that our plant roots are bathed in, and surface waters that our fish are swimming in, they're really close. And so we just take it as being the same thing. Then that means, takes us to the next step in the sort of unpacking the pH symbol. And the pH symbol is the negative log, base 10, of the hydrogen ion, and in this case, these brackets mean activity. And so it's the sort of from the math standpoint, it's the power that you put 10 to in order to come up with the number. The pH scale runs from 0 to 14. We probably all know that. 7 is neutral. This is an old acid rain slide, but we had some examples on it of, you know, I almost guarantee my coffee this morning was down here someplace with lemon juice and vinegar. You know, in this zone, fish start to die, and certain, you know, stream macroinvertebrates are affected. And then up here is, so this is the acidic end, and then up here is the alkaline, or the basic end of the scale, and things like ammonia or lye, or very caustic substances. You know, a lot of biology likes to live in this circumneutral zone. A lot of crops were grown pH 6 to 7, etc. But our soils, as we'll see, range throughout this range, and as well slightly above 7. So this number is the negative log, and so it's kind of the number of zeros for the amount of hydrogen that's in a solution. So pH of 7 is 0. Count 7 out, 0.00001 moles of hydrogen per liter. So it's a little tiny bit of hydrogen. So that's number one. And number two, each unit of pH change is a 10-fold change, because it's a log scale. So if we go from pH 7 to 6, it's 10 times more acidic. If we go from pH 7 to 5, it's 100 times more acidic. If we go from pH 7 to 4, it's 1,000 times more acidic. And so when we see these different pH is in the environment, these aren't simple linear steps of change. They're logarithmic steps of change, and not at all uncommon to see pretty rapid swings from of several units of pH in nature, either as a result of our management, treating soils or disturbing soils. Snow melt and the spring floods create this in streams, et cetera, et cetera. So there are big changes in the amount of hydrogen that take place. So that's kind of what the pH symbol is about. Now we'll just go back to talking about pH and acidity, but with a little bit more insight of technically what does pH represent. And we use, from a practical standpoint, we really use this scale of 0 to 14 and think of pH as whole numbers, not as the small decimal that it would represent if you expressed it as moles per liter, which is the measurement that would be used. So, and I should mention, if anyone has questions, I can't see everyone, so you have to make a noise or something, but if anyone has questions while we go, by all means. Although this would be a lot more fun in sitting on a blueberry field and cherry field or something. Types of acidity, when we talk about soils, and you asked the soils guy to talk, so we're going to talk about soils. We recognize formally 3 different types of acidity. Active acidity, which is if if it rains on a soil and you put a pH probe in there, you're going to measure a certain amount of hydrogen that's automatically just jumps into solution. That's the active acidity. It's immediately available, and immediately impactful to roots and microbes, what have you. The second one is exchangeable acidity. And we'll talk a little bit more. A lot of you know what that's about, but exchangeable acidity is all the acidity that's still stuck to soil particles. It doesn't automatically just jump into solution when the soil wets up, but it's there and readily available to replace the hydrogen that's in the solution. So when we add water to a soil and stick an electrode in, we measure this, but when we manage it, we really try and manage this, because if you don't manage this, this is changed, it's very poorly buffered. It changes very quickly and easily. And this we'll see is really all the exchangeable hydrogen and aluminum that's stuck to soil colloids, soil exchange sites. And then finally, there's the residual acidity. The residual acidity is not all that soluble, not all that readily available. It is much slower to react, but these are all proportional, and this one will replace this one, which will replace this one over time. Exchangeable acidity will replace active acidity pretty fast, almost in real time. Residual acidity, not so much. However, if you have a large pool of residual acidity, you're going to be battling the exchangeable acidity, presuming you're trying to manage acidity, for a longer period of time. And these are just very ballpark, but if we standardize active acidity as 1, how big is exchangeable acidity compared to active acidity? Well, it's 100 times or more. And residual acidity is thousands of times the size, the absolute size, but again, with much less reactivity. So we're not just talking about one kind of acidity. We have these sort of different phases. They're interactive and they're all linked. And some are more immediate, and some are more important for management, and some are more important, sort of the scientists looking at soil formation, development, those kinds of things. So why are Maine soils acidic? And people, I usually do it playfully, but people like to say, oh, those, nasty acid soils of Maine, they just dissolve acid. Well, that's not true. None of our soils dissolve and create acidity any more than alkaline soils and carbonates and limestones do in areas, which we have some of, in areas that are dominated by limestone. The reason our soils are acidic is because we have so much rain that they are heavily leached. And a lot of our soils, a lot of our aluminosilicate soils, the granites and things like that, they weather slowly. If you grind up limestone and you grind up granite and you put it in a beaker with acid and you come back in a month, both will have neutralized the acid. But if you come back in a day, the limestone will have neutralized the acid and the granite won't have gotten that far in neutralizing the acid yet, because it takes a lot longer. It's a harder rock. It's slower to weather. And so that's the major reason. That's nice background. That's the major reason that our soils are acidic. So leaching is really important. If our soils weren't leached, if we didn't get more precipitation than evapotranspiration, if we had more evapotranspiration than precipitation, then things that dissolved would stay there. We'd accumulate salts because the water would evaporate and the salts would stay there, just like making rock candy, or salty water drying up on the countertop. But we have a constant sort of leaching front because we have a lot more rain than we have evapotranspiration, or the energy to evaporate. And so we're constantly washing through our soil. And that's how we get acid soils. We then add to that some of these other mechanisms. We get a lot of our of acids from organic matter decomposition. And we get our acids from organic matter decomposition in 2 ways. Number one, as the organic matter decomposes, it creates organic acids. That's that brown humic acids and fulvic acids that we see in surface waters and the foam in the river and the spring. That's not pollutants, it's organics coming out of the woods and the forests. They're not fully decomposed. They've been mobilized from the organic matter. We have a lot of them. They're weak acids. And so that's why I can drink coffee at pH 2.5. It's all organic acids and it's weak acids. If I tried to do that with hydrochloric acid at 2.5, we wouldn't be having this conversation. So these weak organic acids provide a lot of hydrogen, but they're not as aggressive as a mineral acid would be. So one, we get a lot of weak organic acids as organic matter starts to decompose. And so that drives and creates acidity. And then number two, as the organic matter is decomposing, microorganisms in the soil, bacteria and fungi, are consuming the organic matter. I mean, when we put a mulch on a soil and come back and we have to put more mulch next year or add organic amendment to the soil, it's because the microbes are decomposing that organic matter. When they do that, they do the same thing we do. They use enzymes in their bodies to oxidize the organics, use the energy from the oxidized, primarily carbon, and release the carbon dioxide as a waste product. And so in soils, we have a pretty high partial pressure of gaseous CO2, particularly during the growing season, the more active it is. And so what happens is that CO2 that's released from microbes that are decomposing organic matter, some of it goes to the atmosphere, some of it dissolves in the water, the soil water. And if you add CO2 to water, and you add a little root beer flavor, you end up with root beer here. If you just have water, you end up with carbonated water. And that will combine to form carbonic acid, which is what this is. Carbonic acid is, just like organic acids, a weak acid. It's not an organic acid, though it's the only mineral acid that is common out there that's that weak. And so weak acid meaning it wants to give up one of its hydrogen. And so in the typical soil pH ranges that we're working in, it gives up this one hydrogen, and then the bicarbonate runs around as an anion and creates, therefore, another source of hydrogen. So you have these weak organic acids giving up hydrogen, and you have carbonic acid giving up hydrogen. And so here comes, we have water moving through the soil. We have these processes creating a lot of hydrogen. And then the hydrogen starts to interact with soil particles that drives kind of the acidification process. One of the big things that happens is that these hydrogens push off or undergo cation exchange with the base cations, calcium, magnesium, potassium, sodium, and pushes off from the soil surface. The hydrogen gets adsorbed. Now these are in solution. If it's leaching, they're constantly being pushed through the soil system with just a couple of exceptions. If plant roots take them up, they're biocycled. And if microbes take them up, they're biocycled. Stay in the soil, but nevertheless, they're biocycled. So as soon as the hydrogen pushes the base cations off into soil solution, they're either going to be leached or they're going to be taken up. And if they're leached, they're gone forever. And in fact, that constant leaching has depleted over time these base cations faster than they can be replaced by weathering. And so that gives us our acidic soil environment. When I say these are lost, I'm not talking about the calcium that's still buried in a piece of granite, because that's going to be here for a long time. Just the calcium, magnesium, potassium, sodium that are loosely held, exchangeable on the outside of soil particles. But once they get bumped off, they're going to go somewhere, and either they're going to be what we say biologically immobilized, or they're going to be leached. Where am I here? At the same time, many of our soils, and certainly many of the soils, most of the soils down east, are what we call aluminosilicates, meaning the building blocks of the mineralogy of the soil is aluminum, silica, kind of tied together with oxygen, and everything else is a sort of secondary impurity in the mineral itself. So we have a lot of aluminum and silica that are the building blocks of our soils. And what happens with the addition of this acidity is it accelerates the release of some aluminum from weathering. So as there's more acidity, the weathering of these aluminosilicate rocks occurs faster. These base cations are more easily leached than the aluminum, and so we tend to accumulate the aluminum. And over time, we're continuously stripping away the base cations, kind of the nutrients we want for crops, and we're accumulating aluminum, which is a classic characteristic of our acid soils, our acid podzols around the world, and certainly here in Maine. So the kind of the picture here is, leaching is driving all of this in one direction down through the soil. We're producing acidity from, at least naturally, from organic acids, and that's the dominant, or organic acids in the CO2. And that ends up mobilizing the base cations into solution, being replaced by the hydrogen and accelerating the weathering of release of aluminum, but aluminum will tend to accumulate. And so our soils are accumulating aluminum and being depleted in base cations. And we use, in this part of sort of soil chemistry and soil science, we think of hydrogen and aluminum as the acidic cations, and these four, calcium, magnesium, potassium, and sodium, as the base cations, or the alkaline cations. We also create acidity with some of the nitrogen fertilizers, and nitrification as a process of organic nitrogen turns into ammonium, NH4, turns into nitrate, NO3, and in those steps, we create acidity, actually kind of 2 to 1, 2 moles of hydrogen for every 1 of nitrogen that goes through that process. So depending on the fertilizer that we add, we can be exacerbating or adding to the acidification of the soils. Of course, if you want to acidify your soil and add nitrogen, then it's doing both at once. And then litter quality. This is not a really. I put it on the list because it's important to think about. It's really these mechanisms embedded in the characteristics of litter. But what I'm talking about here is in any sort of plant community, whether it's blueberries, corn, or spruce fir, plants are growing, plant components are coming back to the soil, that's the litter. And this biocycling we talked about, in some plant communities, it's pretty effective. And so there's a lot of nutrients being taken up, and therefore the foliage has pretty high concentrations of these nutrients. Most crop plants are in that category. And so when that litter falls back to the soil surface, it contains a lot of those base cations. As it's decomposing, it releases those back into the soil. And if there's plant roots there to take it up again, you have a nice mechanism to retain those base cations in the system so they don't leach. If you remove the crop, then you've taken the base cations away. And if you cut off the uptake, so if you remove the crop so the roots aren't taking up the base cations, then they'll leach away. And a lot of times we do both. We harvest the crop, shuts down the uptake, and we've removed the crop and the nutrients that are in it, and so we can exacerbate it. So litter quality can have an important role. It's in forests. I would talk about the difference between spruce fir, softwood, and hardwood trees, and natural or extensively managed stands. pH is always higher in a coniferous forest than it is in a deciduous forest. pH is always, lower. Acidity is higher. because the litter quality ecologically is poorer in spruce fir or even pine. So if you put a pine bark mulch on compared to a composted manure, the pine bark mulch is going to tend to acidify because it's not giving you many base cations and it's giving you organic acids, whereas the composted manure is chock full of good nutrients as it decomposes. And then the last one in my list is acid rain. I did a lot in acid rain for a long time and sort of still do. It's all rolled into other environmental change for experience. But I would often get asked, are soils acid because of acid rain, and how much does that contribute? Acid rain was really important and remains of importance, not as important as it used to be for sure, which is a good thing. But it really didn't acidify the soils. The big impact of acid rain was what the sulfate did moving through our soils, and the addition of the nitrogen, which would lead to some level of acidification, but particularly in managed croplands, it was too poorly buffered. It had low pH, but it was too poorly buffered to really move the needle on pH. And so we weren't seeing a decline in pH in our soils because of acid rain, but anywhere east of the Mississippi River, I could show you the chemical signature of the acid rain in the chemistry of sulfur and nitrogen. So that's the answer to why our soils, Maine soils, acidic. It's all of it's driven by the leaching front moving relentlessly in one direction, and the interplay between the base cations and aluminum and hydrogen. Okay, so switching gears, how am I doing on time? Okay. This part is sort of who cares. So this is the correlations with acidity, and I'll kind of walk through why we're interested in pH. And from a chemical standpoint, from a chemical property standpoint, pH is by far the longest used soil chemical property that we test for and that we use for interpretations, because we knew how to measure it, a century and a half ago with pretty good accuracy, and we observed some of the things that we're going to talk about here relative to the relationships. So when we measure pH, without measuring all the rest of this, we often can surmise a lot of this information, and we do. So number one is pH is highly correlated or related to exchangeable base cations. And this figure here, it's a little busy, but bear with me. Here's soil pH along the x-axis, the bottom here. And this is the percent of the cation holding capacity. If you know what cation exchange capacity is, it's the percent of the CEC. But it's basically the percent of how many of these sort of loosely held cations are occupied by these different constituents on the soil. So most of the action in soils takes place by chemistry at the surface, and soil surfaces are negatively charged, net negatively charged at least. And so they're interacting with positively charged ions in solution. And that's why we're talking about calcium, magnesium. You see they've got, these are all positively charged, and the aluminum is positively charged. And we're only talking about positively charged because the soil is negatively charged, and opposites in this case attract. And so the positive and the negative sort of stick to each other. The anions, the negatively charged, these cations are not running around in solution by themselves. So there's either hydroxyl or carboxyl or organic anions to balance the charge. Otherwise, we'd have sparks coming out of the ground. But they're moving through solution, or they're interacting in some other way with the soil. These exchange surfaces are primarily interacting with these positively charged ions. Okay, so message here is this is showing you the this surface right here is showing you the total sort of net negative charge on the soil that changes as pH changes. And so as pH goes up, we have more and more of that negative charge. And we'll talk a little bit about that in a couple of minutes. And we call that property cation exchange capacity. It's the amount of this negative charge. And what we're interested in soils is the balance between the acidic cations, primarily aluminum, and a little bit hydrogen. So this shape represents the aluminum. This shape represents the proportion that's hydrogen. And see down here at pH 3, there's a big area for aluminum, decent sized area for hydrogen, and then the base cations in this soil example are just this little component. As pH goes up, the total amount of this charge increases, and it is increasingly dominated by the base cations. And pretty much once you get above pH 5.5, aluminum disappears. Exchangeable aluminum, reactive aluminum, it's still there, but nevertheless, it disappears. That becomes a really, really important feature of the chemistry of aluminum. We'll talk about that in a second. And so that's all that this is showing you, that as pH goes up, the amount of these exchangeable base cations increases. We call it base saturation increases, and meaning they're more available, they're more dominant, and there's less acidity around. And that correlation is really, really strong. In fact, a lot of times in simple testing algorithms in soil testing labs, they just do a linear regression between the percent base saturation and the pH for a given soil, and can predict, usually with pretty good accuracy, the amount of the base cations just by measuring pH, because measuring these is routinely done, but it's still a more complicated process than a simple pH. And so we see that, from pH 4 to pH 7, we go from about 40% of it dominated by base cations, to pH 7, 100% is base cations, and we just end up going up from there. This table is a little busier than we need for the point being made, but why I'm showing it to you is these are all names of different types of clays, not ones that we have, not all that we have here in Maine. We have a little bit we don't have many true clays, secondary clays here in Maine because our soils are so young. We have a little illite, we have a little vermiculite, a touch of kaolinite, and we really don't have, we have secondary versions of these compounds, but it's primarily these kinds of clays that we have. Out in the Corn Belt in the Midwest might have a lot of these kinds of clays, and then of course this represents organic colloids, so the tiny parts of organic matter that act like the clays in holding on to nutrients. And what this table shows is that there's a component or a portion of the cation exchange sites on these different kinds of clays that are sensitive to pH. That's why, if I can jump back, whoop, that's a sneak preview. Oh boy, I guess I didn't. No. What did I do? There we go. Okay, what I wanted to do, go to there. That's why this surface is increasing. This is the total amount of charge. This is that residual acidity, but it's not contributing to exchange acidity. And so it's really this surface that is increasing as pH goes up. And that's because a portion of the exchange sites on these clays are pH dependent, meaning as pH goes up, they change. And here's pH 7, the cation exchange capacity of these different sort of colloids, small particles in soils. Organic colloids have a high cation exchange capacity. That's why when we add organic matter to our soil, we hold on to a lot more nutrients and water and other things, but the nutrients are due to this. These kinds of clays, a lot of you know what vermiculite is, potting medium, or use it for packaging the squishy stuff. But as a soil clay, it's got a really high cation exchange capacity and ability to hold on to nutrients. But most of the clays that we have in our soils are sort of down here, and we also have a low clay. Some of the charge on these clays is pH independent, meaning no matter what you do to pH, it's not going to change. And the majority of the charge in these kinds of clays is pH independent, more so for the clays that we have. Almost none of organic matter is pH independent, meaning pH can go up and down. The amount of that cation exchange capacity stays the same. The real message here is that this column is the pH dependent charge, meaning as pH goes up and down, this is the proportion of the total charge that will increase and decrease along with that pH. And you can see that organic matter is almost all pH dependent. So when you lime a soil and the pH goes up, the cation exchange capacity goes up. And a lot of that's due to organic matter that's changing its total net charge as a result of pH. These clays don't have very much at all. That's dependent on pH. These other clays that we have small components of in our soils have a fair amount of pH dependent charge. If we were in the southeast of the US, we'd have a ton of this stuff all through the southeast coastal plain. And they have a lot of kaolinite, and it dominates in those ultisols. And highly pH dependent, but we pretty much are sort of in this range, and so we only have a little bit of the change that's coming from our mineral clays. So all of that, the take-home message is that organic matter dominates. There's a little bit of contribution from the clays, but that as pH goes up, the total amount of cation exchange capacity can go up significantly, and as pH goes down or we acidify, we reduce the ability of our soil to hold on to those nutrients. Okay. And wherever there isn't a base cation, there has to be an acidic cation. So whatever the negative charge on the soil is, if it's 10, we won't use units for the, if we go from 60% of that base saturation down to 40% base saturation, we've got to increase the acid saturation. We've got to increase the amount of hydrogen and aluminum, because as we lose the base cations, we gain hydrogen and aluminum on those exchange sites. Okay, I'm going to take a minute on this figure because I like it so much. This is a solubility curve. But it's not as sort of annoying as it might seem at first. Here's our pH scale, which we are familiar with, 0 to 14, circumneutral about here. The only thing we really need to know about this figure is that this, as we go from here upwards on the y-axis, it's an increase in the solubility, meaning it dissolves, it weathers more easily. Chemically, it's more prone to weathering. And what I'm showing you are two curves. One is the solubility of silica, which is the natural characteristics of silica in the environment, and the solubility of aluminum, which we've been talking a lot about. And these two curves explain a lot about how our soils, our acid soils, form. So up here in really high pH, where our soils almost never are, both are pretty soluble, meaning they'll dissolve. You'll find a lot in solution. They're easily mobilized. As pH decreases, or as you decline, go down in the pH scale, more into the sort of circumneutral soil zone, you see two things happen. Well, three. Both of them become much less soluble. So they're much less likely to dissolve, And if they're in solution, they're probably going to precipitate. Okay, so if a parcel of water moves into a soil that was up here and it comes down here, that aluminum is going to precipitate and accumulate in the soil. The second thing is you'll see that both of them do that, but silica is a little more soluble at all pHs. And we see that all around us. There's a little bit of silicic acid in water everywhere, in the tap, in the stream, in groundwater, even a little trace of it in the rain, because all these aluminosilicate minerals are releasing silica, and a little bit remains soluble and forms the silicic acid. Aluminum in this mid-range, very insoluble, so it's going to want to precipitate until you get down to about pH 5.5. Once you get down to about pH 5.5, silica's puttering along the same way, but aluminum suddenly becomes way more soluble. And that's a really important threshold in our soils, because as we manage our soils up in this range, we really don't have to worry about aluminum all that much. It's not soluble. If you let it to its own devices, it's going to precipitate and accumulate. But if our soils drift down below this pH range, suddenly the aluminum starts to be soluble. And as you can see in this figure, it really just comes pouring out. And so in these acid mineral soils, not the organic soils, not a peat bog, but in the acid mineral soils that are formed in rocks and minerals that are below this pH threshold, aluminum rules. And we'll see that in a minute. So this solubility difference is important. And I know everyone in the Zoom is familiar with the Maine state soil and knows that it's Chesuncook, but in case you didn't, Chesuncook is the Maine state soil. This is a picture of a Chesuncook soil profile. And I'll tell you why I'm showing you this now. So it's a forest soil. It's mostly in forests. This is what we call the O horizon, the forest floor. We have a little one in blueberry fields as well. In an undisturbed forest soil, a lot of them in Maine, we're going to have what we call an E horizon, this white ashy colored layer. There's usually a really abrupt boundary between these two. And so that's pretty remarkable relative to what roots have to sort of navigate through, going from this essentially peat bog kind of material, organic O horizon, that's part of the soil, to this totally different mineral E horizon. And then another big abrupt transition to this part, which is the B horizon, and then finally down here to the parent material that keeps on going. Why am I showing you this? I'm showing you this because as the rain impacts this forest floor, it creates a lot of those organic acids that we talked about. And so you have this really acidic solution, and the first mineral soil that it impacts is this zone. And this zone exists because of that phenomenon. So you have a lot of acids, they're still in their acidic form, they're pretty aggressive at weathering, and they really scour this area. However, and therefore they sort of tear apart the mineral structure. The only thing that gets left behind is the silica. And why these things turn ash white is it's sort of an accumulation of quartz. Now, most of ours aren't old enough to really be just quartz, but they're on their way to that. And lots of everything else has been stripped off. The aluminum's been mobilized, and all the cations and everything that was in there have dissolved. As it keeps on moving down with all the aluminum, and the pH starts to increase because we're neutralizing the acidity. And when you get down into this zone, the pH is high enough that all the iron and aluminum, because iron does the same thing as aluminum, it's just not as concentrated, precipitates, and that gives us this reddish color. Where the reddish color is an indication that the iron and aluminum is precipitating. We can see the red like rust. We can't see the aluminum, but chemically there's way more aluminum So they're both doing the same thing. So the differences in solubility that we saw on that last curve, because this is really acidic, because that solution coming out of the forest floor, those organic acids are down here in pH. This aluminum is just really soluble. It's taking off. But there's enough insoluble silica that we're leaving behind some silica to create that E horizon. Everything else is moving out, and then the rest gets distributed or leached out of the soil profile. I'm not going to take time to do this. I'll just quickly say why we call aluminum an acidic cation is because when you put aluminum that is released from a mineral, it's aluminum trivalent +3. And if there's water around, so there's plenty of water around, it will undergo these hydrolysis steps and produce 3 moles of hydrogen. And so the hydrolysis of aluminum is very effective at creating more hydrogen from the interaction between water and that metal. And this is precipitated aluminum, and that's what's accumulating in the B horizon. Okay. So we can come back to that if you have questions, but it's a really important buffering mechanism and an acidic component of our soils. This is, I'm going to show you 2 examples of sort of the typical composition of the cations on the surfaces of a soil, the occupation of the cation exchange capacity. If we sent it to the lab and they measured it and they said, well, you have this much exchangeable A, B, and C. The classic agricultural soil may or may not be blueberry. I look to you folks to say that, but the typical AP horizon in a garden soil or a backyard would have this. These are percentages. I don't know why this percent's down there, but would have this distribution of the different cations. And so if you add, calcium is about 65%, magnesium is about 10%. So we need a lot of calcium. It's used for structural components of plant material, and plant demand is relatively high compared to these other cations. Potassium and sodium are usually just a few percent. Calcium, magnesium, and potassium are essential plant nutrients. Sodium is not. And so if you add these together, you come up with about 80% is base saturated. So 80% of the soil colloid surfaces, the cation exchange capacity, are base cations in these circumneutral agricultural soils, and about 20% is acidic. And that's kind of the model for the typical productive agricultural soil. We have a little bit of acidity kicking around, strongly dominated by calcium, and about 80% base saturated, which is going to give you a pH, because they're highly correlated, of near neutral. This is a forest soil, pretty typical forest soil. These are the data from Beddington, but I've done soils all over the state, and it kind of looks different. So these are just different depth increments in the soil profile. Here's our O horizon, and sort of in a forest, and maybe at times in blueberry, the O horizon has a really low pH. It's down in the 3s. It's not anywhere near 7, but it's governed by organic acidity. And so our plant roots can tolerate that way better than they could tolerate, which they wouldn't be able to tolerate, a mineral acidity like sulfuric or nitric or hydrochloric acid. And if we look at the composition of the cation exchange complex here, you see you got a lot of hydrogen because it's organics, and so you have a lot of that available hydrogen that comes from organic functional groups. You have a fair amount of aluminum, but even though the pH is low, we have a lot of calcium, fair amount of magnesium, and potassium. And in forests, the roots of the plants are really relying on this O horizon for a lot of the available nutrition. Because, as you can see, even though the pH is higher at depth, the exchange sites are almost totally dominated by aluminum. And so this yellow is aluminum. This is nothing close to what we saw with the agricultural soil. And so in mineral soils, acid mineral soils, below pH 5.5, this is what you're going to get. You're going to get it predominantly aluminum, a little bit of iron, but iron's not as concentrated and it's reactive at a lower pH range. So most of the action that we deal with in management is aluminum. And in fact, a lot of times you're liming a soil not to decrease the hydrogen, just to deactivate the aluminum. Because aluminum, it's not an essential nutrient for sure. It's trivalent, so it's pretty aggressive. And it is usually, it can often be damaging to tissues. The reason acid rain was killing fish in the Adirondack was because aluminum was getting on the fish gills. And the reason that aluminum bothers plants is because it damages fine roots and those more sensitive tissues. Okay, I'll move right along. Factors correlated with pH. Nitrogen's correlated with pH, but because of a completely different reason. The transfer of organic matter, nitrogen, to, again, ammonium and nitrate all depends on microbes, primarily bacteria are the most effective at it, and they are really sensitive to pH. And we'll see that in a slide in a couple of minutes. But for the sake of time, nitrogen availability is directly correlated with pH, but not because of this cation exchange phenomenon, because of the impact on biology, specifically microbiology. Phosphorus is correlated with pH because of, not the biology, it is a little bit the same mechanism as nitrogen. So we get some phosphorus from organic matter decomposition, but primarily it's a function of not exchangeable chemistry, not this biology, but the precipitation and solubility of specific compounds in our soils. And this figure sort of says it all. Phosphorus in the soil is most available in this circumneutral pH range, between 6 and 7. And the reason being, as pH increases above 7, the propensity for calcium and magnesium, actually, to combine with phosphorus and precipitate, making the phosphorus unavailable, goes up dramatically. So if you overlime a soil, you can immobilize your available phosphorus. It's still there, it's just it's not available to be taken up because it's locked up in a chemical precipitate with calcium. More often, we're in an acid soil environment, and you've heard me enough talking about this already. Here's the aluminum range, here's the iron range, so you see it's active at a much lower pH. And as soon as we get below, again, down to here about 5.5, you can see aluminum is really very active. This has it a little more reactive above 6 than I probably would have drawn the curve. But nevertheless, as pH goes down, aluminum combines with phosphorus and is very effective at fixing it, precipitating it, and it makes it unavailable. In fact, we use that in an environmental way. If you can get leaching waters to percolate through your soil, our soils, rather than over them, you're not going to have a phosphorus problem in the associated surface water, because all the phosphorus is going to get fixed in the B horizon with all that aluminum. It's really a very powerful immobilization mechanism. And so pH gets really important then, targeting the pH relative to phosphorus availability. And the lower the pH, the more you're going to have to either add an organic source or an inorganic source of phosphorus to overcome this fixation capacity. Micronutrients are needed in really small quantities. Here are some of them. They're all metals: cobalt, copper, iron, manganese, nickel, zinc. And they're all metals that sort of behave like aluminum and iron. All of them have the same chemistry in different ranges, and that's why as pH goes up, remember aluminum deactivates as we get above pH 5.5, these deactivate. If pH goes down, these become more mobile. So if you lime your soil from, 5 up to 7, you could find a micronutrient concern. Doesn't mean that they're not there. It just means that you've now precipitated them, probably as a hydroxide form, because of the pH change. And the only micronutrient that is the exception to the rule, because it's not that kind of metal, is molybdenum, MO, because it runs around as an anion, molybdate anion, and it kind of behaves like phosphorus in that regard, or phosphate in that regard. So take home message, pH goes up, micronutrients become less available, macronutrients become more available. pH goes down, the opposite occurs. I keep doing that. And then finally, soil biology, which affects organic matter decomposition, the mineralization of nitrogen, the mineralization of phosphorus. This is kind of the take-home message. Bacteria are way better at doing whatever they do. So they're way better at decomposing. They're way better at transforming nitrogen to an available form. They're way better at decomposing organic matter and mineralizing phosphorus, meaning that they're more efficient and they can outcompete everything else when the conditions are right. And the conditions are right by way of pH between 6 and 8 for these. Actinomycetes are a secondary player. The real competitor here is fungi. Fungi can't compete with bacteria circumneutral, so ag soils are going to be dominated by bacteria. But as pH starts to decline, so as you get below pH 6, now all those biologically driven mechanisms slow down, because now you're more and more depending on fungi to do the heavy lifting. And fungi are always there. They'll decompose the lignins and the hemicelluloses, the tough stuff, but the bacteria is going to take all the good stuff if the pH is right. If the pH goes down, now you're depending on the fungi to do it all. And they will, but they do it much more slowly. And so that's why you're going to accumulate organic matter in an acid soil environment where it would decompose much more quickly in a circumneutral kind of soil. So those are the factors correlated with pH and why we sort of care about it. You'll see these kinds of tables that the bar gets thicker and thinner, whether it's more or less available. That basically summarizes everything we were talking about. We measure acidity. I know you all measure acidity, so there's no rocket science here. We measure it. We have colorimetric methods, pH tape, nice, simple, inexpensive. In modern times, we have these little gadgets that we put in our pockets. Just because it gives you an answer to the 100th doesn't mean it's the right answer to the 100ths for these little gadgets. Colorimetric tests, which are the sort of long-term standby. And then this is kind of the gold standard. pH, not this particular one, but pH meters in a laboratory with an electrode that has ion selective glass at the end of it that's sensitive to hydrogen activity, and we get really accurate measurements of pH. That said, a lot of times people will feel like, I've got to have this kind of a measurement, and realize that every time you take one step in your field, the pH is going to change by a fair, hundredths to tenths of a unit. And so the pH of your soil for a given area is some sort of an average of that variation. And in that context, these kinds of colorimetric tests are really pretty good to give you a ballpark pH of a soil or a field in that regard. You don't need the expensive stuff, certainly all the time. However, obviously it's good to have the standard soil tests to validate that. So, managing soil pH, which you all do. Kind of no-brainer here. We can increase soil pH by adding lime. We can add ash. Be careful what the ash is of and what's in it, but it's a more complicated mix. It's not all nice, pure calcium carbonate, but it's got a lot of nutrients in it. Can have other stuff. It can create nutrient imbalances, but it also can provide the alkalinity of lime, as well as giving you some nutrients along the way. And organic matter, depending on the quality, can also raise the pH. On the flip side, what do we use to reduce soil pH? Sulfur is kind of one of the classics that I usually point to blueberries as one of the crop cultures that utilize that. And organic matter, but not the same quality organic matters, a different kind of organic matter with lower base cations can also be used to reduce the pH of the soil. So with that, this is just the picture of the reaction of we add lime to a soil, the calcium replaces the hydrogen, so now the calcium is stuck to the soil, which is a good thing. It's in water, so the hydrogen is released and forms carbonic acid. The carbonic acid in most pH ranges that we have in our soils won't stay as carbonic acid. It'll decompose, release the hydrogen, and eventually sort of break down to water and CO2. We release the CO2 and we're left behind with this soil particle that now is a much happier place for microbes and roots with a lot of calcium as compared to how it started with a lot of hydrogen and therefore very acidic. So that's kind of a cartoon of the classic liming function. So with that, I'm going to stop and look at Lily. I can talk about Bear Brook, or we've already gone to 5.
Well, let's see if there's some questions first.
Sure.
Maybe. I know, so people are curious about the biology part, especially, I think. And so there's a question, is this why our mycorrhizae are partnering with the blueberry plant because fungi are functioning at this lower pH? So yes, I think so. But is there anything else that you have to add about fungi at this acidity?
Well, I'm not a microbiologist,
Yeah.
so that's the classic cop-out disclaimer. No, I mean the mycorrhizae are really a critical part of those root systems. They are going to be content to be living in the lower pH, and so they can thrive in that kind of culture. They are going to be less likely to flourish the higher the nutrient loading. And so you can decrease the efficacy of mycorrhizal infection by increasing the amount of nitrogen loading to the system. And so, kind of working at odds with yourself in that regard, but they're relatively resistant to the acidity. You get low enough pH, then the aluminum. They don't like aluminum, but they're relative. At least the ectos. Blueberries are ectos.
Yeah.
Yeah. At least the ectos are pretty resistant to the aluminum. The endos are not as much. So
we may have both, actually.
Well,
I should look.
Yeah, what I've learned, and again, not I have one grad student that's doing some mycorrhizal work, but is when the microbiologists look, they find both everywhere. It's just there's a predominance of ectos on blueberries and beech and spruce, and there's a predominance of endos on most of our crop plants. But it seems like the inoculum is everywhere. So they are quite tolerant of these kinds of soils, unless you got really acidic. But they are inhibited by, I think they've evolved to benefit the plants through the symbiosis because they get nutrients for the plants and they use the carbohydrates of the plant. So if you add a lot of nutrients already, then they're less likely to, or they're less prone to be abundant, and it's going to inhibit their inoculation.
Right. Right, so I know that, but I'm just gonna repeat it for the group. When you apply, similar to in a hay crop where you have root nodules on the roots that are fixing nitrogen with the plant, if you add nitrogen or a fertilizer, the fungi or bacteria is no longer benefiting from the relationship because the soil contains that fertilizer that they're going to take from the soil, so they don't have to partner with the plant. And we do have a few more questions. These are good questions. Can we use irrigation to produce leaching to lower our pH naturally? So wild blueberry growers are applying sulfur to reduce the weed pressure in the field. What do you think?
Yeah, sure. I think, yes, the acidity, the acidification of soils from the standpoint of soil development is directly proportional to the amount of leaching relative to the climate they're in. It can be kind of an expensive way to acidify. So, I think if you just try and do it with leaching as compared to adding sulfur and leaching, or using nitrogen fertilizer and add salt, that kind of, I think you've got to keep the leaching pressure going in order for that to succeed. But in theory, I haven't done it. This guy sitting at a desk in the basement of Deering Hall says, yeah, you should.
In terms of weed management, to get an even, consistent pH, I would think it would be might be easier to do it with sulfur if you don't already have a pond or irrigation set up.
Yeah.
But I haven't tried it either, so I don't know.
Yeah.
It's a good idea.
Yeah, I don't have, direct that kind of direct experience. It takes a lot to saturate your soil, the entire soil column, so that you're driving a leaching front through the system. You think about soils, they're probably a little less so on the barrens, but they're about half pore space. And the rest of it is solid particles, all arranged. But if you add up all the little tiny pores, for a cubic meter of soil, half the cubic meter is the cumulative pore space. And so when I think about that, how much water is it? So that means you've got to add enough water to be sure you fill up all those pore spaces, and keep doing that over and over so that this pore space volume is pushing out the next one to keep that leaching front going. And if you look out on your field and you think, a half-meter depth of water is going to move through that meter, that's a lot of water. And
yeah,
it's just, I think it's probably much less practical than combining that with treating it with sulfur.
Yeah. Okay, so are mycorrhizae something that you can apply to your field? So yes, you can apply them to the field. There are products you can buy. However, our system has been found to not really show a significant benefit in terms of yield. Could have other benefits we haven't observed yet, but past research from Jax Magula showed that our soils already have the mycorrhizae that they are going to use. And if you were to add more, it didn't increase yield or production.
Which makes sense. I would just add that the forestry world kind of went through that as well. There was a period of trying to inoculate seedlings with mycorrhizae to enhance their growth, and a lot of the literature just showed the inoculum is all over the place. So adding it really doesn't enhance kind of productivity, and so that wouldn't be surprising to hear that in blueberries either.
Okay, good. Yeah, that makes sense. Someone's asking, what organic matter reduces pH? I guess you said just in general, organic matter is releasing acids. Is there a certain?
Yeah, so you probably maybe you'll identify with it more in a sort of horticultural sense, but you know, pine bark mulch, pine needles, peat moss, all of them have, for a given, you know, for a pound of that organic matter, the concentration of calcium, magnesium, potassium, the base cations, the concentrations are really low. And therefore, as those kinds of materials decompose, they release organic acids in the acid form. So they're running around with the hydrogen on their reactive groups. If you go to a composted barnyard manure, it's the opposite. And so you've got organic matter, but it's really rich in these nutrients. So as it's decomposing, it's not running around as hydrogen with the rest of the organic molecule. It's running around as calcium, magnesium, and the rest of the organic molecule. And so that's going to raise the pH. So anything that's sort of ecologically low quality, I mean, they're ecologically important just the way they are, kind of thing. But you know, wood chips and some of them will tie up nitrogen as well as acidify, and so big time. So that you want to sort of have a strategy there and how you're using it. But those are the kinds that will acidify soil.
Yeah, that's good. We do apply a lot of mulch. And so could you describe the effects on the soil profile and acidity during a drought?
Well, there's a couple of things. The drought's not going to change the acidity all that much. Sort of the amount of acidity that's there is there. However, as that film of water gets thinner and thinner around all the soil particles that our little roots are sitting in, it's concentrating the composition, and relatively speaking, the acidity is going to be increasing because of kind of the thermodynamics of aluminum and what happens with activity as you et cetera, et cetera. Plus, everything's just getting more concentrated. So the plant is probably suffering the most, or undoubtedly suffering the most from the moisture deficit. But if it's an acid environment, if it's below pH 7, it's going to become more acidic. If it's above pH 7, it's going to become less acidic because you're concentrating what's already there. So it's a little bit of a double whammy. It's not a bless. You know, the base cations are also getting more concentrated, but the hydrogen and aluminum are winning that battle. But usually it's just the moisture effect that gets them.
Interesting. Yeah. Do we have a history of the overall pH of our fields since we started primarily mowing fields? We can look back. We do have some of that data from the soil lab. Does it help or hurt to even, does it help or hurt or affect the pH? Okay, so does mowing and how does mowing and burning impact pH? I think, so mowing is going to build your organic matter. And burning, I would think, is increasing your pH slightly.
Yeah, for sure. I suspect both will, because when you're mowing, you're putting a lot of the good high quality tissues, the leaves, you know, on the soil to decompose. But the burning is likely to increase it even more. That would be mine.
Why is that? What's happening when a field is burned?
You're creating oxides and hydroxides of all those metals. And so think sodium hydroxide, you know, it's high pH, it's very alkaline. And so when you burn it, the ash that's left is calcium oxide and potassium oxide. And those are very alkaline, raising the pH. The carbon's gone, you know, you blow off all the carbon. Obviously some charcoal is part of it. It's not a complete burn.
Yeah, I'm curious what the charcoal. does,
Say it again.
because with the natural burn, there's quite a bit of charcoal.
Yeah. So it probably is beneficial in that it's going to stick around for a long time. It probably will break into finer pieces and become intimately mixed in the soil, but that stuff sticks around. The microparticles of char stay in soils for a long time. And it should increase the ability to hold water. It should increase the ability to hold nutrients. So it should have a positive impact in that regard. If there's a lot of it on the surface when you're done, it's going to warm up the soil because of the darker surface. But I suspect that that's probably not the persistent after effect of most blueberry field burning. It's not even in a forest fire burning. It gets mixed in quick.
Yeah. So
speaking of, if I can just tell you one anecdote. So in my watershed, it's up in Bennington, that not far from you folks. I found in some of the soil pits, research pits we were digging, little chunks of charcoal every now and then. So I radiocarbon dated one of those, and the radiocarbon date of that charcoal in that O horizon was 8,000 years old, and it came from the period in the Holocene where it was drier, and so we had a lot of fires in this part of the world at that point in time. But that also means that little piece of charcoal fell into the forest floor, and for 8,000 years, the O horizon built up and decomposed and cycled around, but that little charcoal stayed at the surface, and there was no mixing with the mineral soil beneath it. So we don't have earthworms. We don't have any critters you wouldn't have that E horizon, the profile I showed you, if you had macroinvertebrates and earthworms moving back and forth. So all of which is to say, the charcoal is going to stay around for a long time.
Right. Yeah. Which is so interesting because Ivan is interested in using biochar to apply to blueberry or other ag soils to retain moisture. And that's very interesting because it is a material that would stick around like forever. That's another talk. I was just thinking about burning, and so when we burn, there is a flush of certain nutrients, cations, on the surface. And anecdotally, some growers will say that right after a burn, their plants look very vigorous and very happy. There are a few reasons why that could be. But are these nutrients staying right on the surface, or does it depend how hard you burn?
Yeah, so my thought would be, so you burn, you create some of these oxides of these nutrients that stick around in sort of little granules of the material, but you also mobilize a lot of the cations as well. So you're going to get a flush of calcium, magnesium, potassium, and sodium. When you burn off and you lose the carbon that doesn't stay as char. If it was completely burned, complete oxidation, all the carbon's gone. Some of it doesn't completely oxidize, and so we get a lot of the char that remain. And you lose all your nitrogen. So the two things that you lose from fire is carbon and nitrogen. All the other nutrients stick around. Because of the flush of the base cations and because of that sudden alkalinity that will raise the pH, you're probably going to spin up nitrogen mineralization. So even though you burned off the nitrogen, you may be getting a flush of nitrogen coming out of the organic matter that's decomposing because you just lifted the pH, a pH unit or something like that.
Right.
And the way you did that is giving it all these mobile cations. And so not only does it have nitrogen, the plants have mobile cations. So there might be a really temporary happy place there that is from the base cations that are released. And even though you lost nitrogen, the nitrogen now you've mobilized that was kind of there to start with.
Wow.
Can I ask, So I understand the ashes raise pH, but what does the charcoal itself do pH-wise?
Nothing. So
Okay, neutral.
just new carbon by itself, charred carbon, with a low oxygen and hydrogen count like that, it doesn't change the pH.
Awesome.
Most of the time when we add a char or biochar as a soil amendment, it increases the pH because it's come from a fire process that's created these caustic materials along with it. But pure char itself is not changing the pH.
Any other questions? You can feel free to speak up if you just want to say something. This has been very, very good, very interesting. I think it is probably quite advanced for some of our beginner growers, but it's really good for them to hear because this is like the foundation of our crop. And if you want to do like a brief Bear Brook summary,
Yep.
Go for it.
Really, really fast, just because it's in your neighborhood.
Yeah. I think people would be interested.
Okay, so I threw this in because if we had time, because it has to do with acidification and acidity and all the stuff that we're talking about. We did this experiment for the last 30 plus years, called the Bear Brook Watershed in Maine, and that's Lead Mountain. You probably, a lot of you know it. It's right off Route 9. Go up by the Forest Ranger station and up the road there. And there's a cell phone tower at the top, and those folks hate me, but that's beside the point. And we started this as an acid rain experiment back in the 1980s. And the interest was by EPA to go to some place that wasn't yet heavily impacted, because we're at the end of the pipeline up here, to do some experimental additions of sort of artificial acidity and do lots of research to understand the processes to sort of drive policies. So I'll just give you a quick, where this is. People know where Bar Harbor is, so that's where Lead Mountain is. There's Lead Mountain. This is the summit of Lead Mountain, and this is looking towards Acadia National Park, probably looking towards some of you. And when I get talks, this is a very old slide, but that's where all the lobster restaurants are. When you give a slide at a national meeting, that they know that. Oh, I know Acadia. I know the lobster restaurants. So what we did is there's two watersheds on the side of this mountain that we delineated, meaning all the rain that falls in this one drains right here. There's a stream running through here, and likewise for this West Bear and East Bear. These little two divots in the forest, I'll show you a picture of them in a minute, but those are V-notch weirs, so we measure everything that comes out, and we had ways to measure everything that went in. East Bear Brook was our reference. We didn't manipulate it. West Bear Brook, we treated with nitrogen and sulfur as ammonium sulfate, nothing magical. But that is a form of pollution as well, form of the acid rain kind of pollution. And we did that by flying, here's a picture of the V-notch weirs. So it's like a big swimming pool that measures accurately the amount of water, and we measure the chemistry of what goes out. That's just a cartoon of it. Those are the weirs. Every 2 months for 27 years, starting in 1989, we would fly a helicopter and treat the West Bear watershed with ammonium nitrate as our acid rain treatment. And we were sort of creating a watershed that was like New York or West Virginia, which was more polluted at the time, with East Bear being our reference. We stopped in 2016, and the goal of a watershed like this is kind of like a black box. We measure what goes in, we measure what comes out, and so we have a perfect sort of control on inputs and outputs of that system, and then we get inside the box and we measure all sorts of stuff. And so we do research on why it's changing, the way it's changing. A lot of this influenced management and forestry. It influenced policy relative to air pollution, what have you. And this little cartoon is kind of our conceptual framework of a drop of water coming through. It's interacting with the forest canopy and soils and on down through the system, finally gets to the stream, and then of course it goes out to Narraguagus and out to the ocean. We're not gonna stop there. I'll show you this slide. It's the long-term data for the stream chemistry. This is the reference watershed, and this is the treated watershed. And so you can see what we induced over almost 30 years. They both were very similar before we came along, and then in 1989 we started this acid rain experiment and added ammonium sulfate. And this plot is sulfate, this plot is nitrate in the stream. And what you see here is, to no surprise, the red is West Bear, and we added the sulfate and it increased dramatically. It increased up to, don't worry about the units, but it increased up to 200. Interestingly, the models that Congress was using for the Clean Air Act reauthorization in 1990 were wrong, because they would have predicted this would have gone to 300. And so those are the kinds of things that we learned from these studies. And then importantly, if you see this is East Bear. This is the reference watershed, the reference stream. And why this is important is because this is the effect of the Clean Air Act. We reduced sulfur in our emissions, that we reduced the air pollution that came up the prevailing winds to us from all the way, the Ohio River Valley up through the mid-Atlantic and into New England. And what we see over those 3 decades is a steady decline of this pollutant in our streams. And all over the eastern United States, we have evidence that of this cleanup. It's not all gone. If we just came along and measured this, we'd say, oh my gosh, it's really polluted. But wow, are we way ahead of where we were back in the 1980s. And once we got up to an equilibrium, the treated watershed just tracked it. Same thing with nitrate. Well, not same thing, a little different with nitrate. And nitrate, outside of it early on, which is a different problem or different issue, you see the blue is really low. We don't get much nitrate coming out of our watersheds because our landscape's nitrogen deficient. So the trees are all using the nitrogen, even when we're adding it as a pollutant treatment. But when we added the ammonium, it was transformed into nitrate by those microorganisms we talked about. And we see a sort of steady trend of the nitrate. This line here and here is 2016. And what we see is that for nitrate, as soon as we stopped treating, the nitrate in the stream went away. So it was overnight recovery for the stream. The forest will be cycling it for the next 500 years, but not the stream. In sulfate, this is West Bear. We stopped treating right here. It went down, but it's still way above the reference watershed, the natural conditions. And point of that is it's going to take decades for us to recover because a lot of the sulfate is stored in the soil. In fact, I'm not very good at this, am I? This is a plot of the concentration of sulfate in the reference watershed with depth in the soil and in the treated watershed. And you can see this big bulge in the B horizon, all that aluminum that we talked about that grabs onto phosphorus, it also grabs onto sulfate. And so it's accumulated here, and we're gonna have to slowly bleed this out before those ecosystems will have recovered. And those are the kinds of things that we can provide to policy. So we did a stable isotope experiment where we treated the entire watershed system with 15N, and that's a natural, it's not radioactive, but we can track that nitrogen through the ecosystem. we didn't need to get into all of that, but it's expensive. Back in 2011, I spent $118,000 on these 5 buckets of ammonium sulfate fertilizer, but all of the nitrogen in it was heavy nitrogen, N15, so that we could use that to treat the entire watershed and then track it. And we're still able to go track it. And, you know, my granddaughter can go track it when she's a famous soil scientist someday herself. And just to give you a last show and tell here. So this was the several days that we treated it. Those are big cattle watering tubs that we use to collect water by our streams. Then we had hundreds of these buckets all over the watershed that we would use to fill up backpack sprayers. And see that little bottle there? That bottle would have a little bit of spike. That's about a $300 bottle right there of the heavy N15. We'd pour it in and then dilute it with stream water that came out of those buckets. And then we would traverse the watershed with backpack sprayers, usually as a team of 3 going through the woods. And that's the map I took a picture of that we used for that experiment. It took us 5 days. We walked like 60 miles, going back and forth across the watershed, treating it with N15. And then we went ahead and did the experiment to begin to track it and see how it moves and how it moves differently in the 2 watersheds. And that's the crew on the last day when we were done treating it. I'm glad I got a picture because I was shocked that they were still smiling. But so this experiment's going on Lead Mountain there that many of you probably drive by, and it has been for 30 years. And at a lower ebb, we're still doing work and sampling there. All right.
Awesome.
I'll quit.
Any questions about that? Or anything else you thought of?
Jim's got a question.
Yeah, Jim, do you have to unmute yourself? Should be a microphone in the bottom left corner of your screen to click. You could always type it into the chat box if that was easier for you. There we go.
Okay, I can just ask him. I'm a mulch guy, so we know the pine bark is better. Where do wood chips fall into this thing? And what other options are there for mulch to decrease pH?
That's a good question. I don't know the answer. I don't know that wood chips are dramatically different from pine bark mulch. Pine bark mulch has a higher nutrient content, even though it's really low nutrient content and it acidifies. And so I'm guessing I haven't seen people using it too much because it's going to decompose really slow. So if you want it to react and give you the acidification effect, and perhaps, you know, add organic matter to the soil, the wood chips are going to be very slow, and they're really going to tie up the nitrogen as compared to pine bark. You know, peat moss is pretty acidic. It's really low pH, very low nutrient content. It's kind of expensive for a extensive field mulch scenario. Pine needles, conifer needles are good in that regard. Yeah, but I'm not familiar. Some of the, I mean, Lily and Dave and other people on the phone here.
I mean, the pine bark mulch is really the best thing we've got. You can, you know, we are currently doing an experiment comparing different particle sizes of pine bark mulch or pine mulch. So we have a sawdust, a shaving, a bark, and a chunk, or what you would think of as a chunky mulch. Becky's on here. She's my master's student doing that work. So Go Becky. Yeah, it's that's, you know, for a long time we have recommended people to apply the softwood mulch. So we're just trying to look into more detail about what particle size might be best if you were to apply it across the whole field for increasing your water retention specifically.
Yeah.
But yeah.
Is there any influence in terms of the thickness or how deep you make the mulch? Can you make it too thick, or if you make it too thick, does it slow it down too much, or what would be the theoretically the ideal thickness of the mulch?
So there are a lot of factors. Historically, we have recommended mulch as a practice to apply to bare patches, and that is recommended at a thickness of 2 to 4 inches. And that's very thick and probably not economical to apply to a whole field. So in these new times where we want to hold on to more water in the field, there's got to be a sweet spot less than 2 inches where, you know, it would be economical to apply, but also hold on to enough water in the soil. But in terms of soil chemistry, maybe Ivan can help us understand more about how nitrogen is tied up by these mulches.
Without carrying on too much. So there's this, and some of you I know are familiar with the concept of a carbon-nitrogen ratio, the amount of carbon compared to the amount of nitrogen in any material, a litter or a mulch or what have you. And the wider the carbon-nitrogen ratio, meaning the less nitrogen you have for the amount of carbon that you have, the slower it's going to decompose. So pine bark mulch has probably got a pretty high carbon nitrogen ratio, but probably not as high as wood chips, which to me means a couple things. One is the pine bark mulch is not going to tie up nitrogen as much, and it's going to decompose more quickly. So if you wanted to acidify the soil, sitting up there and not reacting with the soil is not going to get you very much, and that's kind of actual wood chips that's what they're going to do for a long period of time. So you want kind of a balance between not decomposing too quickly and providing acidity, but also not tying up your nitrogen too much because you want it to decompose. So the carbon nitrogen ratio from the standpoint of decomposing and chemically reacting with the soil for the goals that we're talking about here, acidifying, I think the wood chips are probably the worst because they've got the highest carbon nitrogen ratio. They're going to decompose the least. They're going to be the least reactive. They're going to tie up the most nitrogen. And so these other, like pine bark mulch and pine needles and things like that, tend to be, I think, probably what's used the most because you get the happy medium. They have enough nutrients that they will decompose. The quality of the litter, the lignins, et cetera, are such that they're more hospitable to microbes that will decompose them. So they do react to some extent with the soil, but they don't have that much of the base cations, that much nutrients. So when they react, they acidify the soil. It's just not as powerful as, you know, putting flour or sulfur on it, but it obviously does do the job, and it can be expensive.
Say, Evan,
Yeah.
wouldn't sawdust be actually more reactive because there's a lot more surface area, smaller
So,
particles?
Yep, it would. That's absolutely right, Dick. It would also react because it'd be more reactive. It would also asymptotically increase the tying up of nitrogen if you just mixed it with the soil. So there's that downside, the reactivity that you're going for. But yeah, it would react certainly faster for sure.
Hey, Becky, somebody's asking, are there commercial sources of pine bark? Where did you find yours?
Yeah, I found a lot of sources just as byproducts from local lumber companies. So a lot of them will just have the waste that they create for sale as a byproduct. So often you can get it for cheaper that way, rather than going to like a gardening shop or a other type of shop like that.
Yeah, it's big business in the spring. Homeowners and want it for around the house, et cetera. So it becomes quite a guerrilla market out there at times.
Yeah. And Becky made a nice table of pricing for the different particle sizes that we're using from one company, but it does give you a sense of the cost. And you'll find that in this year's annual Wild Blueberry report, which is posted on our website, but it's also on its way to you in the mail, as long as you're on our mailing list. So that's coming to you, which is exciting.
Just a question on the pine bark mulch again, thinking about it. Is there an advantage of aging it for a period of time before you distribute it, or just put it on when you get it from the lumberyard?
That's a really good question. I don't know. I want to say yes to the aging because it'll, sort of be inoculated and kind of punky and integrate with the soil quicker. But the leaching that takes place right at the beginning is leaching out these organic acids that are exactly what you want in your soil if you want it to acidify, if you're doing this to acidify. So I don't know the answer to that. If I had to do it in my backyard, I probably would put them on immediately. So everything that was leaching out would be captured, because those organic acids that we see, in the streams, the brown waters are the organic acids that are leaching out of the bark that's in the woods, and the other stuff that's in the woods, and it's pretty acidic. It'd be great if you could bottle that stuff and use it. So I probably would put it on kind of raw and not composted first.
Thank you.
Yeah, good question though. I don't know for sure I'm right.
Oh, I know Nicholas Lindholm, a grower, did an experiment with ramial wood chips, which would be very young, just chopped birch. I think he could chime in, but and the idea there is that those would not be tying up as much nitrogen because their carbon and nitrogen ratio is so low. But over time, they are getting older, and I think over time they would tie up nitrogen.
So what did it would depend on what they chipped. So if you chip brush that had the leaves still on it, that would be true. If you just chipped wood, not much. It could be green wood, it could be, dried wood. Carbon nitrogen ratio is still pretty up there.
Okay. Nicholas, what did you apply?
Yeah, it was mostly gray birch. And actually the studies out of Quebec kind of predict or define ramial chips as without the leaf on it. So you usually do it in the late winter. My chipper, though, did not have a really fine setting. The chunks probably ended up being 2 inches on average or a little larger. So they're, this is now year 7 or 8, and they're still visibly there on the surface. Yeah. So they are taking a long time.
Yeah, that makes sense. Yeah, I mean, if there's a lot of fine branches have a little lower carbon nitrogen ratio, so that would tip it. But the big chunks like that makes sense.
Yeah, so I think that's a crucial part that my individual chipper just didn't allow the chip size, but the size of the trees themselves needs to be 2 inches or smaller and includes all the small branches.
Yeah, well, that's better at least.
There's one more question. Is peat moss a lot more acidic? Yes. And would it work better for pH? There must be a reason why. Well, so peat is expensive.
Right. That's it. I don't think there's a bigger mystery there.
Yeah. It's
really expensive.
very expensive, very sought after material. So
Yeah.
Um,
Yeah, I mean, it's great because it's kind of uniform, it very naturally acidic, and so it does everything you want it to do, but it's pretty expensive, and there's a lot of sort of ecological concerns with mining peat bogs and
right.
using it for that purpose. So
Yeah.
I don't see that one going anywhere.
Well, thank you so much, Ivan. This has been great. And
Sure, thank you.
yeah, appreciate it. It was a good chemistry talk, and it's good to get the brain moving. So
Great. Well, thanks everyone for having me. I appreciate being here.
yeah, take care, and we'll see you on Friday for disease management.